Hello students, welcome to Advanced Deep Learning Lab. Today we will see the fifth experiment. I'll show you the experiment, that is time series prediction. We should use a deep learning model to predict future values. Example, you can take stock price data or weather pattern. Here in our lab program, we'll take stock price data. First I'll show you the demo, then I'll explain. Now here is the program. This program takes input file, that is stockprice.csv. This is the file name and these are the data. Two columns are there. One is date column, another one is the close price of stock. So we have totally 500 data. Let me explain the program. This import file we know already. NumPy, pandas, matplotlib, min-max scalar we are using. We are building a sequential model. So previous program we have used RNN. Now here we are going to use LSTM. And here we are reading the input file stockprice.csv. The data frame is stored in data frame df. The pre-processing of data, it is converting the entire data to min-max scaling. So we know about min-max scaling. The minimum value and maximum value will be converted to this range, that is -1 to +1. But stock prices are in positive value, but the ranges we have given here -1 to +1, or you can give 0 to 1. So the scaled data is available here. Now here we are creating a sequence. This is the function. I'll move to the next cell. We are taking the input. Our sequence length is constant value, we have taken 60. The scaled data, which is done in the previous cell, we have normalized and scaled, that is taken here. 60 values for x and y we have taken. We are splitting the data for training and testing purpose. 80-20 is our training testing split. So here split is 80. Automatically training will be taken 80, remaining 20 is for testing. Here LSTM model is used. So you can see model, sequential model, LSTM 50 unit, here another LSTM 50 unit, then one dense layer is the output layer. Previously one LSTM, then one more LSTM. This LSTM, first LSTM is having a return sequence true. So the hidden layer will have a return sequence. The second LSTM will not have. By default, this return sequence will be false. Here model compilation, optimizer, like a previous model we have used ADAM, adaptive momentum. Loss function we have used mean squared error. So we are fitting the data here. I have given 40 epoch. You can change the values and check the accuracy. Now the test data is taken. The scaled data for predicted price is assigned to the variable predicted price and actual price. A graph is drawn for both actual price and predicted price. So this LSTM is predicting time series data. Now let us see how this LSTM is predicting. What is the difference between the previous model and this model? Here in this experiment we are using LSTM. Earlier experiment we have used RNN. What is the drawback in RNN? We have vanishing gradient and exploding gradient. So in RNN, you had one input layer and output layer and hidden layer, repeated hidden layer we had. Suppose you are using a lengthy hidden layer. A weight which is used in this layer, for example, this is your current layer, this layer weight, this layer weight, when you want to remember this previous node here, so all this weight you will be considering, right? So if the weight is very small here, that will be multiplied with the previous one. If that is also very small, if you move like this, it may move near to 0, so that leads to vanishing gradient. We have to use a memory part here. LSTM is supporting memory. Even though you had some 100 node before, some information can be retained to your current node. Similar to vanishing gradient, we have exploding gradient also. The same manner, if you have less weight, if you have more weight, 10,000, 100 like that, if that weight is multiplied with the previous node weight, so that may lead to exploding gradient. So to use memory part and to avoid this vanishing gradient and exploding gradient, we are using LSTM from RNN. So we are moving from RNN to LSTM. So LSTM is better for stock prediction. This is your RNN model. This box represents a layer. This is previous layer and next layer. So from previous activation, you are getting input here. Your RNN, standard RNN contains a single layer, that is one tanh function, single layer. Now in LSTM, we'll see, in LSTM, we have 4 interacting layers. So you have your previous activation, this is your next activation. If this is your x of t, the previous is xt minus 1, this is xt plus 1. So the repeated hidden layer you have here. Here 4 different parts are there. So this first part, sigma, multiplication, here addition, and here tanh activation, and top one horizontal line we have. Now we'll see the architecture of LSTM. So LSTM contains a cell state, a single layer. This is a single layer. The previous one is cell state t minus 1, the next state is cell state t. And each cell has these gates and memory. Memory is on top. This horizontal line is memory cell. And here we have gate. Pre-gate is forget gate, first box, input gate, second box, output gate, third box. And the notation is this box represents a layer. This box represents a layer, and this circle represents point operation. If you have vector value, that vector value will be multiplied with another vector, so point operation. And this arrow represents vector transfer, and 2 things are combined. So this corner you can see ht minus 1 and xt, this is combined. So this is concatenation, and in some place it is copying. From one it goes into 2 parts, that is copying. Now we'll see the detail of LSTM. First one is cell state. Cell state, top of this line is called, horizontal line is called memory. It is like a conveyor belt. From a previous node, 50 node before that, some information you had that you want to retain. So like a conveyor belt, same value will be keep on rotating in your cell state. So if anything is required, you can add. If anything is not required, you can remove. So this top one is from previous cell state t minus 1. After removing and adding new value, you can get a current cell state t. That can be given to next cell state. So like that, it keep on rotating. The pattern data, repeated data will be retained, which is not important, that will be removed. So the first part is memory. Second part about gate we'll see, forget get layer. As we have seen three part we have. First one is forget get layer. So on top, this is like a conveyor belt, memory is retaining, and here from previous state you are getting ht minus 1 and this is your input. So it is applied with sigma. So sigmoid activation function we know, it's a new weight, and with h of t minus 1 x your input with bias is given. So that is given to this point operation. So this point operation removes some value. So sigmoid activation range is 0 to 1. If anything has to be removed, it will be 0 or near 0. Anything has to be added, it is 1. For example, if you have 7, 8, 9, 3 value, in 7, 8, 9, you want to retain only 9, 7, 8 you want to remove. So the value will be 0, 0, 1. If 0, 0, 1 is multiplied with 7, 8, 9, first two value will be removed and 9 will be retained. So this is not strict 0 to 1. You may have a value, 0.99 may be a value. In that case, 99% of that information will be retained to your next cell state. So this is your first one, forget get layer. The second one is input layer. So in this cell you can see the previous one is forget get layer. Now that is input layer. Your input is already given, h of t minus 1 is coming here. Now one intermediate value, c cell state t, that is tilted values are calculated. Then c t, that is your input. Your input is x of t, and the previous one is combined here using sigma and tan h function. This formula is used in the previous operation. Now tan h activation is done. So this is your current CT. The next layer is output layer. So output layer is the final layer, will filter all the value. Whatever has to be added, it will add. Whatever has to be removed, it will remove. After that, the final output is coming. The OT is your final output, and this is the third layer. So we have seen the notation. This is concatenation. So here in this part, few things might be removed, and here new things might be added. In our lab experiment, two LSTM model we have used. So the first LSTM, repeated values, repeated hidden nodes are there. So repeatedly it will add the value and remove some value. The final dense layer will take output here, one single output. So this is an example for many to one output. Many values we have, from that some repeated patterns are identified. One output is predicted. And this operation is applied in this function, LSTM function in Keras. So we'll just mention the activation function, and RNN sigmoid function we are mentioning. That's all in the LSTM explanation. I'll show you the program once again. So here is the model, LSTM model. This LSTM model is a sequential model. The first 50 units of LSTM will have a return sequence true. So the repeated patterns of number will be identified in this LSTM 50. That is given to next LSTM 50 node. Here there is no return sequence. So from there the output is given to dense layer. Now you can see the predicted value and the actual value. The red line represents the actual market price and the green line represents predicted price. So that's all in lab experiment 5. You practice this program and upload your document in Google Classroom. Thank you, students.